Thank you very much. So I'm most grateful to Chris Moffat for inviting me in spite of the oddity of my subject. So this work has been done in collaboration with Emmanuel. The things that I'm going to report today, which is more recent, has been done with Emmanuel Faure, Antonin Eddy, Stéphane Perard, and Mathieu Labousse, and then there were other collaborators in previous works. So the whole system, the whole question that I'm going to address is the following. Can any of the phenomena that are supposed to be fundamental in quantum mechanics exist in a classical system? And so we are drawn to asking ourselves this question by the accidental finding of a classical system where a particle couples to a wave. So this is what I'm going to describe. The problem is that some of you have heard this several times, and then the talk becomes longer and longer. So I will present the beginning of the talk very briefly and with films. So I will try to explain the phenomena with films only, and then only the most recent work I will present in the most serious way. So the basic system is very simple. You take a small bath of liquid, actually it's a silicone oil, 20 times the viscosity of water, and you shake it vertically with a vibrating oscillator. So this is a classical system for getting Faraday waves, as I will discuss later. And on this bath, you deposit a small drop of the same liquid. And what happens is that the drop doesn't merge with the substrate, but keep bouncing on the substrate. And this I will show you on films. It's more, it's nicer looking. So, so the first film is a slow motion of what happens. So typically the drop is 1 millimeter in size. The oscillation is 50 Hertz. And as you see, the drop bounces. So the trick is that the drop never touches the oil. There is always an air film separating the drop from the oil. And the air film doesn't have time to break at each collision before the drop lifts again. So the air film is renewed. So for this reason, you can keep the drop bouncing for days if you wish. Okay? 50 Hertz. It can be something else, but in that particular case, it was 50 Hertz. Now, that's also interesting by itself. I can, this actually gives rise to if you put several drops on the same bath, you can, they interact through the waves and they form crystals. I'm not going to show you, I can show you in private, but I have no time to show it to you now. And I'm rather going to show you what happens if I increase the amplitude of forcing. So if I increase the amplitude of forcing, the rebound changes. As you see, the amplitude of the bounce is much larger. The amplitude of the wave is also much larger. And the result is that the bouncing becomes asymmetrical. The drop creates a wave and bounces on the forward front of this wave, therefore falling further on the bath, and this repeats over and over again. So for this reason, the drop does what we call walk. Walks on that. So we will call the whole structure. So I can show you the same film from above, and you can clearly see the asymmetry. Okay. So let me show you this the same film, but now in real time. This was slow motion, you remember. So if you look at in real time, so I'm going to show you the experiment as you see it really. So this is a tank which is about 10 centimeters in size, seen from above in stroboscopic light. And what you see is a drop that moves approximately 2 centimeters per second, which is about 1/10 of the velocity of the wave. It is scaled on the velocity of the wave. And as you see, it moves quite happily, and when it touches the border, it is repelled. And therefore, you can keep it again for a long time, if you wish. Okay, so this, I'm just going to show you briefly, just for the pleasure, what happens when you have two drops on the same bath and you collide them. And so this is one case of collision. So as you have seen, the drop repel each other, and they repel each other without even touching each other, just by the influence of their waves. But that's not the only situation. You can also have this situation where it's very similar collision, but just a different impact parameter. And in that case, you get this. So you get orbits, and in fact, the interaction law between the two drops is periodic because it's through the waves. So you get orbits that are discrete. So this I'm not going to describe today. It's just it was a work done previously by Suzy Protier during her thesis. Now, what I'm going to just show all the films together because it saves time. And so I will discuss a little bit the motion of drops when they are confined in a finite space. So this is the first case. So the circle that you see is a cavity. Outside, on the wall of a cavity are covered by oil, but only a very thin layer. So in fact, the bath is deep in the circle and shallow outside of it. The drop moves, and it's very uninteresting motion. It just follows the border because the waves are repelled. I mean, the waves, they are reflected wave that repel the drop. Now, I do something which I will discuss later on. The same drop, the same cavity, everything is the same. And the trajectory can also be like this. But if you want to know what happens, you have to listen to my talk. Okay, so you see in that case, the drop has a very disordered motion. And this, I will show you why this happens. Okay. So that's all for the show, I think. Yeah. And so I will discuss mainly two aspects. One is the very simple thing: how can the drop walk, and what is the structure of its wave field? So in fact, I'm not going to discuss all the transition to walking. The transition to walking you can analyze as a symmetry breaking, when the bouncing of the drop on the protrusion that it creates is stable for small amplitude and unstable for large amplitude. So when you do large amplitude forcing, and when the waves have a large amplitude, then the bouncing on the top of the wave becomes unstable, and it shifts, and then the drop starts propagating. So these I'm not going to describe, but the rest I will describe. Then I will describe the possibility of having drop doing orbital motion. And then in the end, I will discuss possible relation with quantum mechanics. Okay, so I have to go into a little bit into the technique of the system. So in fact, we fixed all the parameters. We have a given oil, given frequency of forcing. And this is a phase diagram showing what happens as a function of the size of the drop and the acceleration that is imposed to the bath. So below this threshold in the gray region, the acceleration is too small, the drop disappears. In all this region, the drop bounces. And in this region, gray here, you start getting Faraday waves. That is, when you oscillate a bath vertically, it is susceptible of developing Faraday waves, and this is what happens above this threshold. So the Faraday wave, it's maybe important to have a quick recall of the Faraday waves. As you know, above this threshold, you will see standing waves form on the wall bath, and usually these standing waves have a symmetry and that is linked with the boundaries. These Faraday waves have been studied by Benjamin and Ursel, and they show that it's a kind of parametric forcing, and therefore you have resonances at all the multiple of the forcing frequency and subharmonic of the forcing frequency. These are the prediction of Benjamin and Ursel without viscosity. So you see that the waves that you are going to develop have a frequency that is linked with the forcing. And this is a subharmonic, which is a sort of fatter tongue. And with viscosity, then there is a threshold, finite threshold for the formation of the waves, which is here. And you see that the different tongues are different, so that this one is the first to be excited. So this means that when you force the bass at a frequency f0, the waves that are observed are at a frequency f0 over 2. Okay. So let me return to this. No, sorry. Very slow, maybe. Sorry for that. Okay. So in this, this bouncing, in fact, what happens with, now I'll come back to the drop. When the drop bounces, it undergoes a period doubling bifurcation here, so that its period of oscillation becomes half the forcing frequency. And when we reach this region, it is exactly period double. So it means that the drop has the same frequency as the Faraday waves. And therefore, it becomes an efficient emitter of Faraday waves. And this is the reason for which the drop emits efficiently waves, and therefore becomes a walker. So in the yellow region is a region where you see drops walking. Now, if you look at the same drop at various excitation here, you can see that the aspect of the wave field is quite different. Here it's mostly circular waves surrounding the drop. Then you have a sort of horseshoe shape. And here you have a complex structure. The wave field is quite extended and has a complex structure behind the drop. So this is what I'm going to explain, and it's very fundamental for the whole talk. So the question is, okay, the drop emits wave because it bounces repeatedly on the surface. So what is the wave that is emitted at one bounce? So then you don't do it with a drop. You take a small sphere, a small steel ball, and you drop it delicately in the bass, and you look at what happens. So this is what happens in a bass which is motionless. So you just, it's like when you throw a stone in a pond, you have a wave propagating away and fading away. Now if you do the same thing in a bass that is oscillated below the Faraday threshold, you have the same wave propagating away, but it leaves behind a Faraday wave of standing wave that will damp ultimately, but slowly. So if I look at, I can do a spatio-temporal representation of this wave. This time, this space, it's a cut of the previous images. This in the absence of oscillation, you have this propagating wave packet. And with oscillation, you have the same propagative wave packet, leaving behind a packet of standing wave. So you excite locally a Faraday wave mode. So in fact, it doesn't look strange, but it is strange. And I'll tell you why. So I'm just infringing a little bit on quantum mechanics. When de Broglie did his first model saying that there were de Broglie wave, he had this model where he assumed his idea was to try to understand how a particle could be sensitive to remote obstacles without any force in between them. And so he saw that there was some inner frequency in the particle, and that the waves were associated with the particle. And since he wanted to have everything relativistic, his waves were standing waves around the particle. And he had a problem because he had to assume that the wave emitted a wave away, but that there was also a converging wave coming to the particle. And he said that of course, the convergent wave is not obvious from a philosophical point of view, because it's not obvious to have a wave coming from infinity to converge on your particle. But in fact, in our system, it's quite straightforward. The wave doesn't come from infinity. The wave comes from the light cone. It comes from the propagating wave. So you can very easily excite a standing wave without having this paradox of infinity. Okay, so this system where I've shown what the structure of the wave emitted by one bounce. Now I can use it to make a model for the Walker with repeated bounce. So the idea, so this is a numerical model due to Emmanuel Faure. And so there is a model for the bouncing. So the rule globally is that the drop bounces periodically with the forcing that is imposed. It touches the surface. At each time it touches the surface, there is friction. And it rebounds, and its new velocity is the old velocity damped plus a component that is due to the kick it receives at this collision. And this kick takes into account the local slope of the surface. And so depending on the slope, the particle will be kicked left or right. Okay? So of course, it means that at the point where the particle is, you need to compute exactly what the slope. And how do you compute the slope? Well, you have to compute the wave field. And this wave field is not due only to the last bounces, but to many previous bounces. And the question is how many? Well, that depends on the distance to the Faraday instability threshold, because the damping time of the wave is decreases exponentially when you go away from the Faraday threshold, which means that it becomes infinite at the Faraday threshold. So so this led to numerical simulation. You can reproduce easily the wave field. And in fact, the structure of this wave field is in fact very well known. It is the Fresnel interference pattern of sources of circular waves spread along the previous trajectory of the particle. So it's well known in textbook in optics. Some of you must have computed that when they were students. I did, so it was useful. Long time later. So this explains what you see here, what I've shown you previously. This is the structure of the wave field. It's circular here, it's horseshoe. And this is just a matter of how many sources are still active at a given time. So here it's about 5. So it's what we call a low memory regime. We are far from the Faraday threshold. The waves are very strongly damped and they fade away. But the particle still moves. I mean, it's still a Walker, but it's a Walker without a memory. And here, at the other extreme, the particle is sensitive to a wave field which has been accumulated during the past trajectory. In this case, 50 bounce. You can go to 200 in practice. Okay, so now this is very close to Faraday's threshold. So you have a very huge wave field. And you have a problem, which is the following. You have an object which is symbiotic because everything lives together. The wave and the particle live together. They have to move together. And of course, you can do things to the waves and what is going to happen to the particle. Okay? And the other question is, are other stable trajectory possible other than a rectilinear one? Okay, so we did several experiments that I'm not going to discuss, but one of them is aimed at looking at the circular trajectories. So can you do orbiting motion? So there are two ways by which you can force a particle to orbit. One is magnetic. So this is actually inspired by the similarity between magnetic field and rotation that was already used by Michael Berry in his work on Aharonov-Bohm effect. So there is a complete similarity between the effect of magnetic field and a charge and the effect of the Coriolis effect. You can, this is a map of correspondence. If in both cases you get circular trajectories, technically this is a little bit more difficult to do with drops, so we were lazy and we chose this system. So you just rotate the tank you put a walker which has a finite velocity, and you look at the orbit, and indeed, in the rotating frame, the walker does a circular trajectory. Okay, so theory says that it should, when you increase the angular velocity of the tank, the radius of the orbit should vary like this. You do it first with a walker with weak memory, so a walker with local wave field, and in that case it behaves quite classically. There is slight shift, but we know more or less why, but it's too long to discuss. The interesting thing happens when you go to high memory, so your wave is much more extended, in which case you see that you only get discrete orbits. So when you increase the velocity, the orbits jump directly from one radius to the next. So you can repeat the experiment with many different frequencies, different velocity, and you can rescale everything like this. Okay, this is inverting because it's a little bit better to see the steps. Okay, so if you are bored, you can try to compare it to the quantum situation. So the quantum situation is with magnetic field, and it's the situation of lambda levels. So as you know, the Bohr-Sommerfeld condition in magnetic field imposes this quantization, and this gives lambda orbits, and in the real space, the radius of the lambda orbit is given by this formula. So how can you compare it? Because there is a problem, because there is h. And of course, we don't have h in our system, but it's not really a problem, because in our system we have a typical wavelength. And in quantum mechanics, you have de Broglie wavelengths, and de Broglie wavelengths contains h. So instead of expressing these radii as a function of h, you express them as a function of lambda de Broglie. So that gives this. Then you want to shift back to the Coriolis effect, so you have to do this change. And the analogy, if the thing was analogous, you would get that the authorized radius should be like this. So let's see what it does. And as you see, it works in the sense that this formula predicts lines, and the points are aligned on those lines. But there is a difference which lies in the prefactor. The prefactor is not the same. In fact, it comes to saying that in the quantum situation, the perimeter of the orbits is quantized, and in our system, it's the diameter of the orbit which is quantized. Okay, so you can do the numerical simulation, and this helps understanding what happens. In weak memory, you have only few sources there, so it doesn't do much. In large memory, all the points that have been visited in the past on the orbit still emit waves, and you have a coherent wave field which covers the whole orbit. Okay, so in fact, this gives a global structure to the whole wave field. This structure is stable because as the system process, the whole thing rotates. Okay, so in fact, the wave in this situation, the wave exerts on the drop, the global wave exerts on the drop a force which is a function of the diameter, and which goes like this, which is, if you wish, a quantization force, which adds up to the Coriolis force. And if you do the numerical simulation, you get a perfect agreement with the experiment. Okay, so I will now turn to new results. These are sort of last month's result. So the idea is, okay, in previous experiment, you are confined to circular orbits because the Coriolis force or the magnetic force are transverse. So what would it be if you had only a central force? So you try to apply a central force on the drop, which is not so easy to do. So the system we ended up with was to use drops that are formed of two components. So you have the oil drop, and inside the oil drop, you have ferrofluid. You have so it's a magnetic liquid. So it's so the drop contains a liquid which is magnetic. So you have this liquid has to be magnetized, polarized. So you have to apply a global magnetic field, and then you have a small. The drop becomes a small dipole. On this dipole, you can exert a force on. So you put a second magnetic field, which is a small magnet, which creates a gradient of magnetic field, and therefore you get so that's the system. Okay, sorry. As a system, so you exert a central force on the drop. Okay, so in fact, the question what is behind this, you see, because in this new system, I will be able to tune the force that is applied on the drop by tuning the position of the magnet, by tuning the gradient of the magnetic field, if you wish. So therefore, I put the drop in a potential well, that I can tune the potential well. Because in our system, I thought we couldn't ever see a quantization of energy, because the energy, the velocity of the drop is constant, and the wavelength associated to the Walker is also fixed. So in fact, the energy of the system is fixed. Furthermore, it's a dissipative system, so energy is not so clear. But even disregarding this, the energy of so in quantum mechanics, when you do an experiment on a potential well, you have some potential well, and you have different levels of energy, and at these levels of energy are associated different wavelengths. So we can't do that, but what we can do is the following. So our energy is fixed, our wavelength is fixed, but what we can do is change the potential well and look at the different trajectories that you obtain in the different potential wells. And you see that you expect that in this potential well you will see something like this level. In this one you will see something like this level. On this one you will see something like this level. Okay, so it's a trick. So first we do the low memory situation. So as usual, low memory situation is uninteresting. You in a low memory situation, the drop is in the potential well, is blocked in the potential well, and does only circular orbit. We know why. It's only circular orbit that you observe, and the radius of this circular orbit varies continuously with the constant of return of the potential well. So there's nothing special about it. So you can then, so I will skip that, and then you go to a high memory situation. So now I'm going close to Faraday's threshold. You have a long memory of the past, and the general orbit that you see is this. Okay, that's the most common situation. So in the most common situation, as you see, the motion when there is a large memory is very complex. It's very much like what you saw in a cavity previously. Okay, so in fact, it's not entirely true, because you can still recover if you can work at low memory and then increase the memory. And in that case, sometimes you can get the system in a simple situation. So you still have circular orbits like this, even at high memory. Okay? And if you plot them, you plot the size as a function of the potential well, you can see that they form plateau, and these plateaus are the same that we saw previously. They are the circular orbits that we saw in the lambda case. But that's not the end of the story. What excited us was the following, that you see other stable orbits. like this, for instance. So this is also a high memory stable orbit, which is in the shape of a lemniscate. And this lemniscate can be either stable in space, as you see here, or sort of drift also radially very slowly. And if you look, so the next question is it quantized? Does it, and if you look at the typical, oh sorry, it is well fitted by a Bernoulli lemniscate. Incidentally, I don't think it has ever been seen a trajectory with a perfect Bernoulli lemniscate. But if you plot them, if you plot the mean size of this Bernoulli lemniscate, you see that it coincides exactly with the circular orbit of order 2. Now you can go further and you find other stable orbits like the trifolium, like this. And you look again at the typical size of this trifolium, and though it's quite dispersed, you can see that it corresponds approximately to the fourth level. Okay, so now on all these trajectories, you can measure the angular momentum. You know we have all the points of the trajectory, so we measure the angular momentum. So you will, of course, in the circular case, the angular momentum is constant. In the lemniscate, is not constant. It's even reverses. So we don't know why. We believe that there is an exchange of angular momentum between the particle and the wave. But you can do the average. And on the average, when you are on a lemniscate, the angular momentum is 0. Okay, so we do that. We do systematically the average. You find that, okay, on these levels, the angular momentum corresponds to the radius and to the energy. This one is m equals 0. And this one is half as the angular momentum, which is half of that of the circular orbit of the same dimension. And this is in fact very reminiscent of what you see in class. Okay, so this is a sort of diagram showing all the situations that we have seen. This is the first orbit, the second orbit, circular orbit with the lemniscate at. So this is angular momentum. This is more or less something linked with energy. And as you see here, you have the tightest orbit. Here you have the circular orbits of second order with the lemniscate. If you have third orbits and nothing else, we don't know why. And there is the fourth orbit with the trifolia, and then we also see large lemniscates. And the interesting thing is that this structure is exactly that is given in quantum mechanics. If you look at the expected states of in a 2D harmonic potential. In a 2D harmonic potential, the levels that you expect, the states that you expect are n equal 1 or with m equal either plus 1 or minus 1. M equal 2, that would be the lemniscate. This is m equal 3, so this we don't see. M equal 4, here we can see the trifolium and the large lemniscate. So there is a sort of one-to-one, almost one-to-one correspondence. So I don't have much time. So in fact, the sort of very the complex structures. In fact, when you look at in detail at the complex structure and you extract part of the structure, you can see that there are some simple parts in it. So in fact, you can, and in fact, for instance, this one, even though it's a complex structure, it is on this level. So it's a mixture of the degenerate lemniscate with the circular orbit of order 2. So it's, yeah, I have time. Okay, so I will just, so that's the previous part is experimental. Now I'm going into a sort of speculation or conclusions. So because in fact in our system it's clear that we have a particle that is driven by a wave. That's for sure. So in quantum mechanics there are models where a particle is driven by a wave. These are called the pilot wave models, and usually they are not so in fashion, let's put it that way. So in fact, it was initially proposed by de Broglie in his thesis, together with the wavelengths associated with the electron. And then there were many. I have no time to recall the whole story of the evolution of de Broglie's ideas. But in 1952, David Bohm revisited the idea of a pilot wave, but taking for a pilot wave the solution of the Schrödinger equation. And so nowadays people tend to speak of the de Broglie-Bohm approach. And in fact, it's, in my opinion, it's completely wrong because it's completely different approaches. So in fact, the de Broglie approach, so maybe a brief summary is the following. De Broglie thought, the idea of de Broglie was that there was a real wave driving a real particle individually, and that the velocity of the particle was given by a gradient of the phase of the wave. And there was, since after Schrödinger wrote his equation, it was recognized that there were probability waves, and he said, well, maybe there are two solutions. One is the wave at the scale of a single particle, that is a pilot wave, and a second wave, which is a probability wave, and the two waves coexist. That he called it a double solution. It's very much out of fashion in France. Everywhere else, I think also. Bohm used the Madelung transformation of Schrödinger equation, and but you see, Schrödinger equation deals with probabilities, so it gets trajectories. But these trajectories, and this de Broglie remarked, are the trajectories of probabilities, not of any single particle. Okay, so it's in that regard that de Broglie insisted that Bohm's approach was different from his. So so these are different experiments that I didn't show you. One experiment that we did before was a diffraction experiment. So this is actually a numerical simulation of this experiment, but it doesn't matter. These are the trajectories computed for a walker passing through a slit. And as you see, the trajectories are very complex. But as a result, you get statistically a diffraction pattern with the same object. Now, if you look at this experiment, this is a real experiment. So the drop is passing in the slit. If you look at the experiment, you see clearly that there is a wave guiding a particle and passing through the slit. And this wave has this strange structure with this history and this reflected wave on the walls and so on. So it is, in fact, a pilot wave in the sense of de Broglie. Now, if you look at the result, suppose that all the measurements that we have done, we couldn't see the drop or we couldn't see the wave either. But we only knew that there are sources of waves and the receptor of waves. Then we would have concluded that there is a probability, a constant probability of the drops of raining on this slit, and that behind that you had a probability that could be given by this figure, which is the diffraction of the plane wave through the slit. So in fact, we have in that case a situation where this is a first wave, which is a pilot wave, and this is a sort of probability wave. And this is also what we obtained in collaboration with John Bush in MIT. If you look at the cavities, in a given cavity, the trajectory is extremely complex. But if you do the statistics over a long time, you come out with probabilities that are modulated by the eigenmode of the cavity. Again, if you look at one given time in a cavity, the wave looks very strange. You have seen an example at the beginning of my talk, very complex. But if you look at the average, you see the eigenmode of a cavity. It looks again as de Broglie's idea. This would be the pilot wave, and this would be the probability wave. Okay, so now time to conclude. The main drawback of our experiment is it's very, very far from quantum mechanics, and I can sort of list all the differences. So for one thing, of course, it's macroscopic. It has no relation whatsoever with Planck constant. It's two-dimensional. It is dissipative and sustained by forcing. It's not Hamiltonian at all. The forcing imposes a fixed frequency, and the energy of the system and the velocity of the drop is fixed. Finally, the waves, and this is the worst, in fact. The waves live on a material medium, because you have, in this case, there is an ether, if you will. Now, the main interest of this experiment is that it is far from the quantum mechanics, because even though you are far from quantum mechanics, you do recover properties that are those of quantum mechanics, and that is very unexpected. So, in fact, you can comment a little bit. In quantum mechanics, the Planck limitation imposes itself to all phenomena, so it's not possible to do an intrusive, non-intrusive measurement. As you know, all measurements are intrusive, and intrusive produces a projection, as you know. So, in our experiment, we can do either intrusive experiment or non-intrusive experiment, because we can look at the system, and looking at the system doesn't interfere with its dynamics. So, and what we find is that whenever we do non-intrusive observation during an intrusive measurement, for instance, in the case of the slits, then you excite chaotic trajectories, and this sort of is sensitive to eigenmodes of the surroundings. Now, finally, and most important, all the observed phenomena here emerge from what we have called the wave-mediated memory that generates a particular kind of non-locality. Okay, so the Broglie ideas were very unsuccessful. No one ever saw his pilot wave, and furthermore, he never was able to show how the dynamics of this pilot wave could produce the probability. So what relation is there? So this, in our system, we can see with memory, the trajectory tends to become chaotic, and this chaos tend to make the system probabilistic. Thank you very much.
Thank you very much. Each of us has a couple of questions. Please.
Have you tried to spin your droplet to see if there's
it doesn't work because there's too much friction.
But if there's an inner magnetic part,
you
can spin it with a magnet.
You could, yeah, you could. No, we haven't tried. It's complicated enough. But yes, maybe if you have in mind spin, which I suppose you have, in fact there is an analogous of, not quite an analogous of spin, but there is some similarity, because in fact, for instance, if you have several drops, since they are period doubled compared to the forcing, when you have many drops on the same surface, and since they have subharmonic bouncing, they are in two species. The one that bounce on one period and the one that bounce on the other period. So in fact, you have some thing that gives a breaking of symmetry, but it's not the same.
Just a technical one, how do you produce the droplet?
Very simple. You take a toothpick, you plunge it in the bath, and you remove it. You can do it by hand, or you can do it with a mechanical apparatus. But you cannot do it with a pipette, because this produces two big droplets. With a toothpick, you create a small neck, and it breaks, and it produces small droplets. And if you control the depth at which the toothpick goes and the velocity of removal, then you get reproducible droplets. You could also do it with inkjet techniques.
So how many times do you have to do it to get the magnetic material in there and not lose it in the...
Well, some experiments you think are going to be hopeless, like this one. And in fact, it's extremely simple. You put a big drop of ferrofluid at the bottom of the tank in the corner. You put a toothpick, remove it, there's a bridge forming, and this bridge contains a bridge of ferrofluid, so it breaks, and so the problem is how much ferrofluid. So then the problem will begin, and so Stéphane Perard, who did the experiment, was very gifted in finding ways of characterizing each drop. So fortunately, they live long enough, so it's worth characterizing. You characterize them in the morning, and you can work afterwards.
Marie.
Well, just how much time the learning of that trick to achieve kind of average? I want to know if you are.
You mean the ferrofluid trick?
Well, even just the first one, both.
No, not the first one.
The first one
Where
is very trivial.
I don't remember, but I think it was.
I mean, anyone can do it.
Yeah. Well, I can. Yeah. I don't know. Maybe I've. Okay.
Also, we will have other questions.
Yeah.
But okay, it's not.
Well, I'll be here tomorrow, so they can.
Oh, yes, please.
They can make questions that you want in private in my.
Okay, please.
So I was very intrigued by the results you showed where you see this chaotic behavior of the droplets, but then you said that they are made up of these simpler trajectories with the same essentially.
Not always.
Not always, okay.
Not always.
So that seems to draw up an analogy with quantum superposition of states.
Yes.
And then that makes me wonder whether if you make certain measurements, whether you would be able to make the essentially the trajectory collapse onto a state by removing this chaotic behavior through an observation. It would essentially collapse to a simpler orbit.
I think it is very similar. Because what you find is so this is in progress, so I will be happy to discuss, but what we find is that whenever it's very chaotic like this, it's not any chaos. Inside this chaos, you have the two closest eigenmodes. And in particular, in the one that I've shown you, where the size of the trap was right, corresponded to the level of orbits and to the level of lemniscates. Then the mixture was only with those orbits and lemniscates, and for instance, there was no trifolium or no other structure. But of course, there are other cases where it's a bit more complex. And I think it becomes more and more complex when the trap becomes wider. Yes.
Conrad.
Can you do it with a solid object?
We have tried, but it doesn't work. But we didn't try very seriously. So anyone we have not tried very seriously. The idea is that probably solid objects have too rough a surface. So the air film at collision is quite thin. So probably it breaks when with a solid. It would be more convenient to have a small, but it doesn't work.
Because then it could be asymmetric.
No, but if you want to make it as you mean as for the viscosities or things like that, or
No, I mean the object could be asymmetric.
Yeah.
Additional.
Hidden variables.
100 years of work.
Don't make me laughing. We have enough hidden variables, I think.
Maybe, well, so in your apparatus, the bath was fixed, not rotating. I'm just wondering whether, again, if you've tried you could do it slowly, just get some inertial lift, or actually have a curved surface by rotating enough so that it was.
No, it was curved.
It was curved.
It was curved. The surface was parabolic, but it doesn't matter because if you have a drop, a motionless drop bouncing on this parabolic surface, the parabola gives exactly the right impulse to the drop so that it remains on the spot. So in fact, it's neutral. It's actually a chance that the parabola is there because that maintains equilibrium. So you don't have to take into account a centrifugal force. Only Coriolis force counts.
Let's move on. Thank you very much, Yves.
Thank you.